6.2 equilibrium constant. So in 6.1, we'll already learn at equilibrium, concentration reactant and product are constant. Therefore, we will have a constant value. We call it as equilibrium constant. Okay, so equilibrium constant is a constant value where we will take concentration of product divide with concentration of reactant. So concentration of product and concentration of reactant both are at equilibrium. So both of these concentration are at equilibrium. Okay, and then we need to take note the stoichiometric coefficient. Okay, so concentration of C to the power of C here. So any number here. So concentration of D to the power of any number here. Okay, same goes to reactant over concentration of reactant to the stoichiometric coefficient, the value here. And then concentration B to the power of any number here. Okay, so we call it as equilibrium constant. We will take concentration product divided by concentration reactant. Everything must be concentration at equilibrium. Okay. Okay, we have two types of equilibria, which is homogeneous. So homogeneous reactant and product all are in same physical state. So all of them are in gaseous state. Heterogeneous, we will have two or more physical states. Okay, for example, here you have solid and gas, or maybe solid, gas and liquid. So it can have several physical states. So state the type of equilibria for the reaction below. So this one is homogeneous because everything are in gaseous state. This one is also homogeneous, everything are in gaseous state. While these two are heterogeneous because we have several physical state, and same goes to this one. So equilibrium constant K can be expressed into two different terms, which are concentration and pressure. We look at concentration first. We call it as Kc. So equilibrium constant that is being expressed in form of concentration. So for Kc, we will take aqueous and also gaseous state. Aqueous and also gaseous state. Why we'll take aqueous? Because aqueous is referring to solution. Solution is a combination of solute and solvent. So aqueous do have concentration. Okay, for gaseous state, so we know that PV is equal to nRT. So N over V is equal with P over RT. So N over V means that number of mole of gas divided by volume of the container. So this is the concentration for gaseous state. Okay, solid and liquid, there is no concentration. So that's why we cannot take solid or liquid in expression of Kc. For Kp, we only take gaseous state only because only gas has pressure. Okay, gas molecule move random in continuous motion, so they will collide with the wall of the container. So gas do have pressure. Solid is vibrate at its own position. So solid will never collide with wall of container. Liquid will collide but not that much. So liquid, the pressure of liquid is not that much. Okay, so that's why we only consider Kp, equilibrium constant in terms of pressure for gaseous state only. Okay, only gas can collide with the wall of container. Okay, gas will have pressure. Okay. So if we look at the example here, so Kc will take aqueous and also gas. So we will take everything. So concentration of H plus multiply with concentration F minus divided by concentration HF. Okay, for Kp, we also take, we only take gaseous state. So we will take everything. So partial pressure NO to the power of 2. Partial pressure of oxygen divided by partial pressure of NO2 to the power of 2. So Kp is expressed in form of partial pressure. Kc is expressed in form of concentration. Okay, Kc will take aqueous and gas. Kp gas only. Okay, another example for Kc, because Kc take gaseous state, so all of this will be expressed in concentration. So please take note, the stoichiometric coefficient, it will be to the power of. Same goes to this one. Okay, so we look at another example of expression Kc and Kp. Write expression Kc only, Kp only, or both if applicable on the chemical equation. Okay, so for Kc, we will take aqueous and gas, while for Kp, we only take gas. So for Kc, we will consider this one, this one, this one, and this one. For Kp, we will consider all of them. So this is the expression of Kc and also Kp. So for Kp, you can draw the bracket, or if you don't want to draw the bracket, it's also okay. Okay, the bracket means that partial pressure of water to the power of 4 multiplied with partial pressure of carbon dioxide to the power of 3 divided with partial pressure of reactant. So bracket ni just nak bagi tahu nilai partial pressure ni kuasa 4, kuasa 3 lah. Tak nak buat bracket pun tak apa. Okay, next. For Kc, we will take gas and aqueous. And Kp, we only take gaseous state. Okay, so next. So for Kc, we will take gases and aqueous state. So there is nothing at the product side. So that's why it's 1 over concentration SO3. So for Kp is 1 over partial pressure of SO3. Okay, next for number 4. For Kc, we will consider aqueous and gas. So we will take this one. So this is the expression, product divided by reactant. However, for Kp, there is no gaseous state. So there is no expression for Kp. Okay, so for Kc, we will take aqueous and gaseous state. So product divided by reactant, concentration of product divided by reactant. However, for Kp, we only consider gaseous state. So there is nothing in gaseous form for product. So 1 over partial pressure SO3. So Kc, we take gases and aqueous state. For Kp, gases only. Okay, the last one for Kc, we will take aqueous and gases. There is no gaseous state at reactant and product, so that's why there is no Kp. For reaction involving gases, Kp and Kc are not necessarily equal, so the value is not the same. However, if you have Kp, you can calculate Kc. If you have value of Kc, you can calculate Kp. So there is an equation to connect between these two values, Kp and Kc. So this is how we build up the equation to relate Kp and Kc. Step number 1, step number 2, step number 3, step number 4. And then the equation is Kp is equal to Kc bracket RT delta N. R is a gas constant. The value is 0.08206. So T is temperature in unit Kelvin. Okay, so delta N is actually total mole gaseous state of product minus with total mole gaseous state of reactant. So you need to memorize this equation. So make sure KP tu dekat luar. Selalunya kedudukan KC dengan KP ni student tersalah. Macam mana nak ingat? Ingat je, ketua pengawas. Ketua pengawas duduk luar. So, KP is equal to KC and then R and T, you need to multiply first and then baru to the power of. Sebab dia adalah RT bracket to the power of delta N. Kebanyakan pelajar dia hanya dia hanya yang to the power ni hanya untuk temperature sahaja. Salah lah. Okay, so the position of KP and KC, please never ever interchange that one, okay? So KP is equal to KC RT delta N. So we look at example. Consider the following equation. If Kc for the following reaction is 15.35 at 300 degrees Celsius, calculate Kp for the same temperature. So we will use the equation Kp equal to Kc RT delta N. So T must be in unit Kelvin. So I convert 300 degrees Celsius to Kelvin. And then for delta N, okay, delta N, we only consider gaseous state. Okay, so number of mole of product, so here is 2, number of mole of product 2 minus with total mole at reactant. So 1 plus with 3 is equal to 4. Okay, so total mole gaseous state at product minus with total mole gaseous state at reactant. So remember, you need to multiply this one first, then the product of this multiplication to the power of -2. So this is the answer. And then please remember, Kc and Kp, there is no unit for Kc and Kp.